All right, so let's look here at the look at 537. I had too many classes. All right. All right, so here's the algorithm, right? All right. I haven't looked at this guy. You're saying it was hard?
Not as easy as the first one.
Not easy.
Well, it looks easy enough. Okay, got it. Wait, hold on. Where am I? I'm lost. Okay, let's see. So write a program that inputs a string similar to this. So that could be our example input string, right? And apply the shunting yard algorithm to the string to ultimately produce a mathematical result. All right, fair enough. So let's go into Eclipse here. Let's create a new project. CSC537 fall 2015 shunting yard algo. Okay. Create a new class in here. Call this guy driver. All right. All right. So how many hours did you spend on it?
I would guess probably 24 hours.
24 hours of total work?
I would guess so.
And you got it working?
Mm-hmm.
And you spent 8 hours and didn't get it working?
Didn't work.
How many hours did you spend?
Around 15 hours.
15? Does it work?
Yeah.
Well, I didn't sound very confident. What about you?
About 12.
12 hours? Does it work? That also didn't sound very confident.
16 hours.
16? And? It works?
Around like 18, 20 hours.
18 or 20 hours, and does it work? Close? All right, so no, doesn't really work. 12 to 14, and does it work?
Yeah.
Okay.
Around 14 hours.
14, and does it works?
Hope so.
Yeah, all these little qualified answers.
2 days.
2 days, like 48 hours?
No.
See, everybody else is giving their answers in hours. You just give me it in days?
I was not just counting. Maybe 15, 16 or something.
15 or 16 hours, and does it work?
Yeah.
See, that sounded confident. I don't know if I believe her, but it sounded confident. All right, so we had minimum number of hours for somebody getting it working was it?
Blade.
Blade said 24.
Yeah, actually, I'm thinking about it over and over again.
So was it 4?
Time for us to understand what shunting yard algorithm is.
Why? It got pictures here, right?
Yeah,
Look
but
at these pretty pictures.
I almost completed a book writing, drawing, and a program to run.
Really?
Yeah.
Look, here's the algorithm in detail. Tells you what to do.
To write the code when I was drawing the diagrams and all.
All right. Okay, so we have a little under 4 hours, and I got to beat 14 hours.
I'm pretty sure you can finish it.
This is the first time I've never written this.
Be able to complete it in
It's still straightforward algorithm.
Well, let's find out. Okay, so did I have you actually read it in, or I didn't specify?
I just
You could just hard code it in.
yeah, because
All right, good enough.
I just don't want to spend more time.
Nope, fair enough. Okay, so we are going to read something in here. So let's try to understand how this guy works first. All right, let's understand how this dude works first. We always want to draw pictures, so do I not have Keynote open? See, I was thinking about giving you an easy homework assignment for next week, but I'm not thinking about that anymore.
Yeah, give it a harder one.
Yeah, if this one was too easy, I got to do.
Yeah,
This was
Much
not
more.
easy.
it's not hard enough.
So nobody will come here next time.
No. He just hope we will beg him for the answer on Slack.
Yeah, I have to assume the question must be too easy if I'm not getting any questions.
You didn't have time.
You didn't have time to ask questions? There was only 168 hours.
We have other subjects, so it was like.
You have other subjects more important than this one?
No. Half for this subject, half for that subject.
Okay, so fine. So what, 168 says you had 96 hours dedicated for this one. You're only taking one other class?
Yeah.
So two classes.
2 classes.
So 96 hours were dedicated for this assignment.
8 hours of sleep.
That's true.
All right, so 7. Yeah, so I mean, you still have plenty of hours, like 30 hours.
One report. 30.
Oh, the report, that should take 15, 20 minutes.
1 hour, 1 to 2 hours.
All right, so let's look at this guy. All right, so our input's going to look like this. All right, and shunting yard algorithm keeps track of 2 things. We look at the Wikipedia here. We have a stack of operators, and then we have an output string that we're building. Okay, now tell me, as you went through this, what is the output string? How would you describe this guy in the end? What's the format of that output string?
Anyway, I don't use that thing. I just get the result one by one and display the final answer with like a double integer.
Isn't this reverse Polish or postfix notation?
I'm not sure. I don't know the concept.
So our input, this guy, this is infix, right? So the operator is inside the other things. Postfix would say that the operator comes after. Okay, reverse Polish notation is the idea. So what does the shunting yard algorithm do? It takes infix, something that looks like this, and converts it to postfix. And once we have it in postfix, we can use a stack to process it. Okay? So we're going to go ahead and we're going to start parsing this, and but let's do this by hand first. We want to make sure we understand how to apply the algorithm first. Okay? So we're going to start reading through our string, and every single time we hit a number, we're going to add it to our output queue. All right? Every single time we hit an operator, we're going to try to add it to our operator stack, kind of like we did with Towers of Hanoi. Okay, we try to put it on the stack, but certain rules then need to be applied to whether or not it's allowed to go on the stack. Okay, so start walking through this guy. All right, so we're going to call this the output is there, and this is the opstack. All right, we always, since it's a stack, we always push onto the top of the stack. Okay, so we hit a 3. That gets added to our output string like that, right? Then we hit the plus sign. We're going to try to push the plus sign onto our opstack, and we are allowed to do that. There's nothing else on there. Nothing broke the rules, right? Then we hit the 4. I'm going to put spaces in here for right now just so we can kind of see how this works. So we hit the 4. Now we hit the multiplication. We try to push it onto the opstack. Does this guy have a higher precedent than this guy? He does. So we are allowed to do that. Correct? All right. So far, so good. We hit the 2. We add it to our output queue. we hit the slash. We try to push it onto the opstack. Are we allowed to do that?
No,
Why not?
because it has lower than the multiplication. I mean the same.
Same. Less than or equal to? So we deal with this on a left to right basis, correct? If we were walking this by hand, we now know that the multiplication should come before the division, even though these guys have equal precedences. We do equals goes left to right. So before we can do this, we have to pop that off the stack and we add it to our output queue. Then we retry to put the division on there. Are we allowed to this time?
Yes.
Yep, so far so good. Then we hit the opening parenthesis. All right, so opening parenthesis, we try to put that onto the opstack. Is that allowed?
Yes.
No harm, no foul. It's kind of treated as a special case. Okay. Now we hit the 1. Add it there. Now we hit the minus. Try to push it onto the stack. Is that allowed? Uh-oh. Back into the documentation here. Here's our op stack. As we're, let's see, where were we going? Here we read in the this, we push it onto the stack. Read into the 1, we added it to the output. Read in the minus, pushed it onto the stack. That was allowed, right? Added the 5. So this guy has basically no priority, right? An opening parenthesis has no priority. Everything is allowed to go on top of an opening parenthesis. Okay? So we're back here. So we got the 1 here. We hit the minus, push the minus on the stack. That is allowed. We hit the 5. Now we get to the closing parenthesis. What does the closing parenthesis say we should do?
Find the opening.
Oh, I actually put that in the wrong place. Hold on, sorry. Closing parenthesis. We're going to try to push this onto the opstack, and that's going to raise a red flag, right? Closing parenthesis says to do what? Says to continue to pop off the opstack until we hit closing parenthesis. All right, so we're not going to be able to push that guy on there. That wasn't allowed. That's what rose the flag, right? So now we pop off this. Then we pop off this. We hit the closing parenthesis. Now we're done. We popped as far as we're going to pop. Okay? Now what did we do? That was this guy right here. Now we're going to read in this. Try to push it on the stack. Is that allowed?
Yeah.
Yep. Okay. Then we're going to read in the 2. Then we're going to read in another one of these guys. Is that allowed? No. For the same reason that division was not allowed to go on top of multiplication.
It's going through right to left.
Yep, just follow this. So we're going to say no, it's not. Effectively, it will be. But what's going to happen is we're going to pop this
Okay.
and put that here. Then we're going to try to push, and we're still good. Okay? So understand, make sure you understand the operations. Tie, if we have 2 operators that are equal, it's always left to right. Therefore, we cannot push a, quote, disk from Towers of Hanoi on top of another disk of the same size. So we had to pop it first, put it under our output string, and then we can go back in and push. Effectively, in this particular case, the stack looks the same, right? Because they are both the same symbol, whereas in multiplication and division, those guys are equal strengths, but they are different symbols, right? Okay, so then in that case, the order did make a difference.
Now, according to shunting algorithm, it's not this case because it's going through right to left, so it can be added. Oh no, it's not in this case. You can go back to your documentation.
All right, hold on. So you're saying we tried to do this
Yeah.
and put it on there, and that was allowed.
Yeah.
Okay, why?
Because its calculation is going through right to left.
Ah,
Left to
so
right.
this is a different type of calculation.
Yes.
So this guy's a special case.
Yes.
All right, so you're saying that we are allowed to put one of these on top of one of these, but we're not allowed to put a division on top of a multiplication.
Yeah, because that is reading from left to right according to our human.
For how we do the so it would be this. If we're saying this is this value to the second power is left to right.
It's reading from right to left.
how we would do it in reverse Polish. So we're taking this, we're applying this. Let me look at this.
It means actually. It means 6 the. So do to how to say that?
Okay, so this is the associativity. This guy right here. It says that this guy is a right associative.
So you should calculate 8 first, and then this gets 8, and there's 8 and 6.
Fine. This is a value. Oh. Instead of being evaluated, okay, I get it. The reason why the division was not allowed to go on top of the multiplication before is because in that event of a tie, the order of operation says go left to right. In this case, this says go right to left. The order of operation for the power is right to left. Therefore, yeah, got it. So therefore, we are allowed to put it on here, not because we're treating it differently.
Yes.
It's because this operator works differently. The order of operations for this guy is right to left instead of left to right. Okay. So we have we got the 2. We hit this guy. We pushed it on top. Now we get the 3. We're at the end of the string, so now we just start popping. Pop, 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 pop. And that's our reverse Polish, right? So this is what it should convert it to. Make sense? All right. Let's start with just that. Let's just get that part working. Then we'll process it. We're not going to do the math as we go. We're going to actually convert infix to postfix. Make sense? All right. Now, in order to do this, we needed 2 different things. We needed a stack of operators, and we needed a queue. Linked list, same thing, okay? At some point, I'm going to burp here. Just fair warning. And then we need a queue to build up our operators. All right? Now, we do have the issue where we need to be able to split this guy up, right? So we're going to start with this. And I'm going to go ahead and I'm going to right click and we're going to do new class, and we're going to call this guy infix. Well, let's just call it a converter. All right, so converter. This guy's going to have a private string infix, and then we'll have public converter. This guy takes a string infix as a parameter, and we say this dot infix is equal to infix. Okay. Now, when we build our converter, we need to be able to split this guy up into tokens, right? We need to tokenize our guy. Now, everybody in here should have had 535, right? All right. What tool did we learn about in 535 that allows us to split apart strings? One of the assignments in 535 was that one where you had to do like taking a math problem similar to this, right?
Yeah.
And parse it. Okay, and then after you learned about that, we looked at a couple of functions built into Java. One of them was called the string tokenizer.
Um,
Remember the string tokenizer?
I almost forgot.
All right, now we could have written our own here. But the string tokenizer is going to make our life a little bit easier for the splitting this up. It's not that hard of a problem to split it up, right? Okay, but let's remind ourselves how that guy works. So what I'm going to do here is I'm going to have another string. So we're going to have a private, let's call this guy string. Yeah, we'll do a string. Private string called ops. And this guy is going to be equal to plus minus times divide power parenthesis close parenthesis. Anything else that needed to support? Now you could go farther, but is this probably enough for what we're doing? Because if you look at the wiki, you could do sines and cosines and all this stuff. But
Yeah.
as long as we have the associative powers to these things, that we can make it work for anything. So having said that, these are going to be our operators. And then I'm going to go ahead and I'm going to create a string tokenizer. ST is equal to a new string tokenizer. And we're going to tokenize this dot infix on this dot ops. And then the last parameter there is whether or not we want to keep the actual tokens. Okay, and let me show you how this works here. So I need to import java.util to have access to this guy. And if you didn't remember this, you could have certainly written this yourself. It wasn't that horrible of a thing. Okay, so I'm just going to real quickly say while st dot has more tokens, system.out.println st.next token. All right, so let's just prove that this splits that guy up the way we want it to split up. Okay. So we'll go ahead and create a converter. Converter C is equal to new converter. We'll pass out our input. And converter is then going to take in that input, which is assumed to be an infix format. And it's going to create a string tokenizer around that, taking in the infix string, taking in the operators on which we want to parse it. And then, yes, we also want you to return the operators. All right? And what we should get from this, printed out, is a 3, then a plus, then a 4, then a times, then a 2, then a divide, open parenthesis, 1, minus, 5, close parenthesis, power, 2, power, 3. Each one of those on a separate line.
What about the space?
Right now, the spaces I think will be in there because it's going to give us the white space in between. We'll show that as a fix here in a second.
Yeah, space is there.
All right, so those are all our pieces. Okay, so now spaces are gone. Okay, now we do have a couple of empty spaces here though, right? This is a token that is the empty string. That make sense? So we trimmed it. And why is that? Let's look at our original thing. We are splitting this string. We're splitting this string up on all of these individual operators. Now the thing is here is that these two guys here, these guys are two operators in a row. Sitting between these is a space. When I trim the character space, it's going to turn into the empty string. Okay, trimming cuts off white space on either end. This guy is nothing but white space. So it goes from the string with one character in it to the string with 0 characters in it when I trim it. So punchline there is that I want to ignore empty tokens like that, right? So what I'd like to do is I'd like to build up a linked list of all my tokens, things that I can feed off of, right? So as we're going through this algorithm here, what were we doing? We were feeding off this list of tokens.
Yeah.
All right, that makes sense? So as we're adding tokens to this list, we're going to be adding it to the end of the list. Make sense? So let's go ahead and write ourselves a linked list. Let's see, actually. Well, we're going to need it anyways. All right, so we're going to create a class. We'll call this guy a linked list. Our linked list is going to have a private node head. All right, then we need to go ahead and create a node as well. Okay, node is going to have a private string payload and a private node next node, public node string payload, this dot payload is equal to payload, this dot next node is equal to null. All right. Now, as we're building up our list of tokens, we're always going to be adding to the end of this guy, right?
Yeah.
Adding to the end of that list of tokens. All right, so let's go ahead. In our linked list, we'll write our public void addend. And this guy's going to take in a string value. And we're going to walk all the way to the end of our list. So we'll ask the question, if this dot head is equal to null, then, well, we'll always build a node. So we'll say node n is equal to new node value. All right, so if head is equal to null, we'll just point head at the new guide. Else, we need to walk to the end of the list, right? So while curr node dot, well, we need a next node, so we need to teach nodes to give us their next node and also payload. So we'll do a source, generate getters and setters, and let's just get the payload, and we'll do both for nodes. All right, so done with that. Back to our linked list. So while curr node dot get next node is not equal to null, as long as there is a next node, we'll set curr node equal to curr node dot get next node. Okay. Now, one thing I want you to kind of pay attention to here, aren't we pretty much writing the same thing we wrote last class? Which is the same thing we wrote the class before that?
Mhm.
Repetition. We're drilling this over and over and over and over again. Okay. Now, that isn't to say that you can't at some point start using the objects that you already wrote. It's perfectly reasonable to do that. But if you feel that this is a difficult thing for you to do, it will be in your best interest to put in the reps. You know, we talked about a couple classes ago that programming is kind of like a sport. We talked about that last year. Programming is kind of like a sport. Got to put in the reps. We can academically learn how a linked list works. We can even spend 15 hours writing a linked list and getting it to work. Okay? But as we're seeing here, as we're writing this, it's not going to take us 15 hours. It's going to take us like an hour to write the whole thing, right? Something like that. And it's just because we've done these parts in repetition where they just become our go-to moves when we solve problems. All right, so we're going to move curr node into position where we're at a next node that is equal to null. And then we'll say curr node dot set next node equal to n. Make sense? So that's the new end of the list. All right, so that's our end. And then lastly, let's just go ahead, just for testing purposes, go ahead and give ourselves a display. So if head is equal to null, empty list, else, we're going to go ahead and we're going to ask each node to display themselves, right? All right, so we'll teach a node to display themselves. So public void display. All right, and then so we'll say system.out.print this.payload. And then if this dot next node is not equal to null, system.out.print, give us a little arrow dealy, this dot next node dot display. All right. So then what do we do here in linked list? We'll just say this dot head dot display. That should display our list. Make sense? All right, so now let's go back into converter. Right now we're printing out all of our tokens. Instead of doing that, we want to actually keep those tokens and we want to add them to the end of our linked list. So we're going to go ahead and give ourselves a linked list up here. So private linked list. Let's call this guy the tokens is equal to, we'll give it its value in here. This dot the tokens is equal to a new linked list. All right, and then we're going to go ahead and give ourselves a string temp here. And we'll go ahead and say temp is equal to st.nextstring.trim. Because when we say next token, that burns it off of the tokenizer. Okay, so when we ask the tokenizer to give us the next token, it is actually removed from it. The tokenizer is actually a stack. It's popping it off the stack. It's gone. So I'm going to preserve it inside of temp. And then I'm going to say if temp.length is greater than 0, as long as I have something, then I'm going to say this dot the tokens dot addend temp. And then I should be able to display those tokens. Okay, so what does this do here? We tokenize our input string, telling it, yes, I want to keep the operators as well, because those operators are important to us. All right, then we create a little temporary string. We go through as long as we keep having tokens. Let's read in the next token and trim it, get the extraneous spaces off either end. Okay, that way when the user enters in their string, it doesn't have to have spaces. They can put the stuff right next to each other, or they can put 50 spaces in there. Won't matter. As long as what I have is something, go ahead and add it to the end of my list of tokens. Okay, after I've burned through all the tokens, let's ask our newly created linked list to go ahead and display itself. All right, so we have a 3 to a plus to a 4 to a times to a 2 to a slash, so on and so forth. Okay, we got our stuff in the format we need it in. Okay, so this was the first challenge of the assignment, right? To get to this point. All right, now we have the stuff in a way that we can feed off of it. Because the challenge would have been, for some of you, if you didn't use the tokenizer, you had to write your own. And it's possible that your code doesn't work for this now. What if this was 327? And what if this was 28?
I wasted 4 hours for that.
Okay? I don't have to change my code. Code just works. Does that make sense? All right? So, it's a tool you guys were already familiar with, but it's not a tool you've drilled. Right? Okay, so you might have had to write your own. No big deal. I mean, you can sit there and write a string tokenizer in 15 minutes or something like that. But punchline is that I could sit there and write it in 15 minutes. You guys had to spend more time writing it than that because you don't have as many reps in as I do. All right? One of the reasons, and I keep harping on this. One of the reasons I do live programming in class is so you see that it's possible. Does that make sense? You know, I'm not some superhuman and I'm the only person in the world that can write it this quickly. There are other people in the world that can program quickly, but it's going to be people who have a lot of reps in, right? All right, so I'm like a professional basketball player of coding. That's fine, but there's other professional basketball players out there. There are other professional coders out there. You guys can get to that level too. It's reps. Okay, I didn't just pop out of the womb able to write it this quickly, right? I had to suck for a long time. And through repetition, you start building up your tool set. All right, so the very first thing that came to my mind for how to solve this was that tokenizer. Okay, because I've used it 1,000 times. There's another method that you could have used here called split. The string has a method called split, which isn't bad, but I don't think it'll give you the operators. Let me look at this real quick.
But I thought I was not supposed to use it, but I still did.
No, I think split's okay because I introduced split last year after that assignment. Yeah, almost always after I give you an assignment where I intend for you not to use the tool, I then teach you the tool. Yeah, I think it was assignment 2? I think it was assignment 2 in 535, where I think there was a method like what? Print vowels, print consonants, print digits, and then process expression. And the process expression was the one where you didn't have the tokenizer. Then we wrote our own tokenizer. Then I taught you how to do the tokenizer. Make sense? But writing your own wasn't that big a deal. If you forgot it, that for us in here, writing your own tokenizer, fine, took some time, but it should have been more of a tedious act than a hard act. You know, just like, oh, I got to throw a couple hours at this, and you find some stupid bug that you just can't hammer out of there. But it was more of a frustration than a difficult problem. That make sense? All right. Yeah, so split makes sense. Yeah.
So, when I was doing this, I write my own tokenizer, but I am thinking about one problem. If there is a negative value, how to deal with it? Tokenizer.
Yeah, you're right. This guy right here will not work for negative values.
Work with negative values.
Yep. In fact, actually, we'd have to, in order to make it work with negative values at all, you'd have to assume they're spaces. Because what's the difference?
I understand. Separate the number and the operator.
Yep. Yeah. So possible to do, but makes it more complex. So let's keep cooking with this. All right. So we've built up our tokens. So now we have the feed of tokens to feed off of, right? And what are we going to keep doing? We're going to keep removing from the front of that guy, right? Looking at the token and deciding what do I do with this, okay? So I need to go write remove front into my linked list. So if head is equal to null, actually, we don't even need to ask the question. We can just do this. Well, actually, we do need to ask the question. If head is equal to null, let's just return null. Else, string value to return is equal to this dot head dot get there we go. It wasn't kicking in. Get payload. Then we can say this dot head is equal to this dot head dot get next node. So I preserved the payload, adjusted the head of the list, and then I return value to return. That should remove it from the front. Okay? Now, my output queue, output list, we're always adding to the end of that as well, right? When I look at my output guy here, I was always adding to the end of this guy. I always add to the front of opstack. I push onto opstack, but I always add to the end of output. So I already have a linked list that's capable of being my output guy, right? So let's start with this. So we'll go back into converter. We'll say private linked list the output. Okay. So after I filled up that that list, then what am I going to do? Well, let's go ahead and let's give ourselves a function called convert. We didn't have to. You could have done it all in the constructor if we wanted to, but we'll be okay. So we're going to say public string convert. All right, and convert is going to convert this infix string and output a postfix string. All right, so let's go ahead and just say string postfix is equal to the empty string, and at the very bottom we'll say return postfix, and then we'll do our logic here in the middle. We'll build our sandwich. Okay. So in order to do this, we're going to go ahead. We're going to need in fact, actually, I'm not going to do this up here. We'll make it a local variable inside of convert. So we'll say linked list actually, I'm going to keep it. I'm going to keep it global. That way you can fill it up there. All right. So we already know that our what's it called? The tokens is filled up with our tokens. So now we want to start feeding off of that guy until there are no more tokens. Okay? So I need to have the ability to ask our list, is there more? Okay, so I got to put it into our list. And let's just go ahead and write a public boolean has more elements. Okay, and this guy should return true if head is not equal to null and false otherwise. So return this dot head not equal to null. Make sense? So as long as as long as head points to something, I have more elements. So let's test this real quick. So inside a converter, we're just going to go ahead and write a loop while this dot the tokens dot has more elements. Let's just do a system.out.println this dot the tokens dot remove front. Just proving we can get them all off there. Okay, that makes sense? And we'll come back into driver, and now that we've built our converter, we need to say c.convert. And we'll go ahead and run this, and there's all of our tokens ripping off of our guy. And here, I'll put this back. So this was 3 and 2, like that. All right, that makes sense? All right, but now I don't want to just print them out. I want to decide where do I put these, right? Okay, do I put them onto the output list, or do I put them onto the op stack? All right, for right now, let's just build up our output list. We haven't written a stack yet. All right, so let's go in here. So as I'm burning through these guys, each time through, I want to ask myself, so let's just give ourselves a string. Let's call this curr token. And we'll say curr token is equal to this dot the tokens remove first. So we'll go ahead and hold on to that guy. All right, so now we're interested. Is the current token, is the thing that I'm currently looking at, is he one of our operators, or is he something else? Okay? We already have a list of operators up here called ops. So if this dot ops dot index of curr token is not equal to -1, well, let's just say if it is equal to -1, curr token is a number. That's what that says. Index of returns the position within the calling string. So in this case, the position within ops of the first occurrence of curr token. Or it returns a -1 if it was not found. This is ops. So if I look for the number 7 in that string, I won't find it. It's going to return a -1. If I look for a plus sign in that string, it will find it. It'll return a 0. If I look for a minus sign in that string, it will return it. It will find it. It will return a 1. That make sense? So if I get a -1, that means it wasn't one of my ops. And therefore, I can go ahead and just add it to my output. Okay? So let's go ahead and do that part. So we'll say this dot, the output dot, addend curr token. So for right now, after that while loop, if I were to display output, we should literally have just all the numbers, right? This dot the output dot display. This should now give me just the number. Null pointer exception because I removed while ST has more tokens, we went ahead. Oh wait, we're down here. This guy has more elements. We'll grab the current element. So is this guy giving us a final null value? Let's run that real quick. Okay, it wasn't that guy. Let me run this in the debugger quickly. Toggle breakpoint. Let's just see where that guy's coming in. All right, so it has us right here. So let me step over. Where am I? Step over dealies. This guy. All right, so curr token is a 3. That's good. Oh. It dies right off the bat. So that means our remove front must not be working correctly. Is it? Yeah, we tested remove front. Has more elements. Let's run this again. All right, so this is the current value of the tokens. And this has a payload of 3, it's the front. All right, it has to be our remove front, I think. Oh, wait a minute. So this guy, let's see how has more elements works. Let me test this. All right, so this gets us all those values, but it looks like we have one last value. Okay, no, it got us all the values. So remove front indeed gets us all the values, and it has more elements. Okay. And we get the curr token, so this guy should have a real value associated with it. Then we ask if the ops, and index of, okay, so this guy should be fine. So it has to be addend. This should just print out the numbers. Okay, so the problem is in our addend. So let's look at what we've broken in addend. Addend takes in a value. We build our new node around that value. If the head is equal to null, set the head equal to that. Else, curr node starts off at the head. As long as curr node's next node is not equal to null, so we want to get to the end, right? So what curr node dot get next node is not equal to null, set curr node equal to curr node dot get next node. When this while loop is done, curr node should be well, the idea is curr node should be at the last actual node in the list, but we're getting the null pointer exception right here. That's what I'm presuming. And let's look at node. Next node is null by default. Set next node. Let me do this. This dot the output dot display. Let's display it each time through. See what this guy looks like. Oh, we don't even get it the very first time. But the funny thing is we are building up our list here. Okay, so there's the error, so it's here in this guy. Let's toggle that breakpoint and let's debug. This is just adding the original guys on there. Let's just burn through those real quick. Okay. So now we're here. All right.
Can you go back to addend?
Yeah, let me do this real quick. Let me get this guy off. We run this again. Okay, so now we're there. Now let me put the breakpoint back in here. All right, so let's step has more elements. We're good there. Remove front. We're good there. Just step out of that. So step over. So now we're here. All right, so let's step into this. Oh.
First line in addend looks kind of very connected. Return null. Why return null?
Well, this you're talking about addend.
Yeah. Why don't you make the add flux if head equals null? Just go this add front.
We don't have an add front. Well, all we wrote is addend. So we just make head point to the front. All right, so we need to see what's going on in there. So let's run this again, except I need to turn this guy off real quick. Then we can debug it. All right, step over, step over. That was actually interesting. Let's step over that. Curr token is a 3. That's the string 3. Step over. Oh, hold on a second. Remember earlier when I was screwing around saying, oh, do I want the output linked list to be at the top or local? Remember that? Yeah. I never actually gave the output linked list a value. See this guy? Yeah, I probably. Yeah,
Oh, you have an initiative.
No wonder we're getting a null pointer exception. There's nothing in there. So this dot the output is equal to a new linked list. All right. Probably should have a little bit better experience now.
It makes sense.
Try it now.
All right, there's our numbers. Okay. I shouldn't have. I had it initialized, and then I moved it because I decided I wanted it local. And what are you gonna do? All right. So now we got that. So if this is true, we're gonna collect those numbers. Else, if we're in here, curr token is an op. And we have to decide, well, we have to try to push it onto the op stack. Make sense? All right. So now what I'm going to do is to push something onto the a list means to add to the front, right? So I'm just going to go into our linked list here. And we're going to create a public void. Actually, let's do this. Since we're building him specifically for this problem, let's do public boolean push. And we're going to have this guy take in a string op. We'll build our logic into this guy. All right. So for right now, let's just make it always push. All right. So we're going to take in a string. We're going to happen to call it an op here. So I'm going to put a little comment here that this is specific to the shunting yard algorithm. Okay, just like the towers of Hanoi push onto a tower works a certain way, we're going to write our push function here to be aware of how operators work. Make sense? All right, but for right now, let's just make it do a normal push. We won't check to see if it's legal. Let's just get everything pushed onto the stack. All right, so push effectively just adds to the front. So what will we say? We're going to say node n is equal to a new node op. And then we're going to say n dot set next node to this dot head. And then this dot head is equal to n. And then for right now, I'm just always going to return true. Make sense? All right, so this is how we push something onto the front of the stack. I'm not actually testing to see if it's allowed yet, but we're just going to prove that it's doing it. So let's go back into converter. If we're in this else, we need to work with our stack. So we're going to create another private linked list called the opstack. Okay, and then we're going to go ahead and give our opstack a value in here. So if we're in here,
What is the opstack for?
that's going to be our operator stack. This guy right here.
Stack for operator.
Yep. So we're going to say this dot the opstack dot push curr token. All right. Right now we're not actually checking. We're just always pushing it. Each time we go through our original list of tokens, we're going to remove a token. If he is not one of our operators, we're going to add it to the output. If he is one of our operators, we're going to push it onto the opstack, or we're going to try to push it onto the opstack.
Okay.
Make sense? All right. So to test this, let's just display the opstack. Make sure we have a stack of operators. That look like our stack of operators?
Yes.
All right. So we're able to push crap onto the opstack. We're able to add stuff onto the end of the output list, output queue or something like that. Now we need to build in our logic for that opstack. When we try to push something onto the opstack, are we allowed to push it onto the opstack? That make sense? All right. So that means that this dude, let's see, we can put the logic out here, or we can put the logic inside. We know about our operators here. We'll do it on the inside. So in my linked list, I need to make this guy aware of some stuff. He needs to be aware of our operators and their precedences and whether they're left or right. Does that make sense? Okay. So I'm going to have a private the ops, and I'm putting this inside of our linked list. Okay, and this guy's going to have a plus, minus, times, divide. Yeah, we'll just, I'm going to do this a different way. We're going to call this private string the ops. And this is going to be plus, minus, times, divide, power, open, close. Is that it? All right, so that's our ops. Now, these guys have some abilities associated with them as well, right? So private string, or sorry, weight or power, or what did the documentation call it? Precedence. Precedence. I don't like that word. It's a tough word to spell. Precedent. Okay, precedent. Is that it? The press. All right. So plus and minus are 2. Divide times are 3. Power is 4. So 2, 2, 3, 3, 4. And then we're going to call these guys 1, 1. No, we want them to be low, low, low priority. Huh? Right, but we are always allowed to put anything on top of the opening parenthesis. Opening parenthesis is a complete weakling.
Yeah.
That's why we need to make sure he's weaker. We need to probably complete this for this thing here, but we're going to go ahead and we need to know that when we hit that closing parenthesis, that we need to start doing some popping. Does that make sense? Okay, but we just need to make sure that we support that thing there.
So what about if you make the open 1 and the close 5?
Um,
So it'll be lower and the higher. Yeah, 1, 5. Will that work?
well, 1 means we can put it,
Whatever.
actually, hold on. 1 means that it can be put on top of anything, right?
So open should be.
Oh, yeah, this
5.
should be a 5. And this guy should be a, actually, this should be a 6. This should be a 5. So, no, that's not right either. We'll just treat that as a, this is going to be a 5, so we'll definitely open on, and then it doesn't even matter what we make this guy, okay? Because we're going to treat the closing as a special case. Won't matter. All right, so those are the precedences, and now we also need to keep track of the lefts or the rights. That tells us how we do the other part. So string, what do they call it in here? Associativity. The ass. Okay. All right, so the ass is going to be, let's see, so that's everything is left followed by a right. All right, so LLLLR, and then, yeah, those two shouldn't matter, right? All right, so that's the ass. All right, got to have a little humor, right? Okay, so that's those guys. Now, given these things, when we receive an op, we can look up the precedence of that op. We can also check the precedence of the op currently at the top of the stack. Okay, so let's ask this first. So we're going to say, let's see, int. Let's call this top press is equal to integer dot parseInt of. I need to get the top of the stack, so that is this dot head dot get payload. All right, and that guy's going to be an operator. And what do I want to do with that operator? I want to look it up in my ops. So the ops dot index of that operator. This dot the ops dot index of this operator. Okay, so that will give me the position in the ops of that top level operator. And what do I want to do with that guy? I want to get the character at that position in the press. Okay, and that guy is actually a char, so I'm going to concatenate him onto the empty string. So this says, give me the position of the operator at the top of the stack. Then, give me the character associated with his precedence here. Turn that character into a string. So that's going to be like the string 2, or the string 2, or the string 3, so on and so forth. Then turn that into an int. Make sense? That'll give me the number 2, or the number 3, or the so on and so forth. All right, so that's going to be the top precedence. And then we have our new precedence, and our new precedence is going to be the exact same thing here, except we're not going to be looking up the top, we're going to be looking up op. That guy. So now we have the precedence of top and new precedence. We're only allowed to trivially push if new precedence is greater than top precedence, right? We're always allowed to push operators that are more important on top of operators that are less important. Always allowed to do that. So if new press is greater than top press, then go ahead and create the node. Push it onto the stack and return it. All right, trivially. So if it's greater, we don't have to check the left-right crap. We just put it on there if it's greater. Now, if it's equal to, got to check left-right crap, right? If it's equal to, we got to check left-right crap. So, else if new press is equal to top press. Now I need an additional piece of information. Okay? Now, just to make this a little bit cleaner here, let me go ahead and give myself a couple more variables. I'm going to get top pause, and this guy is going to be this guy. And I'm also going to have a new pause. And that's going to be equal to this guy. All right, so now I keep track of the position in my op string of that guy. Then I use that position here. I'm also going to use the position later on. Okay, so same values, I just split it into two lines. So I get the position of the operator in the op string, the top operator in the op string, and then I get its precedent. I get the position of the new operator in the op string, and then I get its precedent. If the new precedent is greater than the top precedent, just add it. I don't need to check anything else. But if they're the same, I need to find out if the top guy is left or right associative, right? So I got to check the ass. All right. So what we're going to do here is let's go ahead and get char top ass. Okay, top ass is going to be this dot the ass dot charat top pause. And then char new ass is this dot the ass dot charat new pause. Okay. Now, if it's right associative, what does that mean? Then we are allowed to push it, right? If it's left, that means we're not. Does that make sense? So, if let's see, the new guy. If the new guy is if the top guy is right associative. So if top ass is equal to R, we can go ahead and push.
Yeah.
Right? So what do? We do this exact same thing right here. Just copy the code, and there's probably a little bit more efficient way of doing it, but screw it. So we'll build it. Then we'll, actually, let's see here. Yeah, whatever. We'll build it. We'll set the next node, add it, return true. Okay. Else, if it's not an R, that means it's the left. I am not allowed to push it. If it's left associative, this push fails. Make sense? So I just return false. Okay. Else here, I return false. So realistically, I could skip this here and just have a catch-all down here that says return false. So if the new precedent is greater than the top precedent, add it, return true. If the new precedent is equal to the top precedent and the top ass is equal to R, it's right associative, also return true. Okay? Still kicking when we get here, return false. I was not able to add him. Now we can compress this a little bit if we take those two variables there and we move it up top. So here, we'll organize this a little bit. So we'll get all the tops there, all the news here. And then this guy can say if new press is greater than top press, or new press is equal to top press and top press is equal to an R. If both of those things are true, then add it. So then I can dump this. So I'll gather all my information about the top, gather all my information about the new guy. If the new guy is greater than the top guy, we'll add it. Or if the new guy and the top guy are the same precedents and the top guy is right associative, then we'll add it. We're still kicking here, return false. We were not allowed to add it. Make sense? So that's our push. Okay, so let's go back into, let's see, oh, I'm missing a semicolon here. All right, so here's all of our operators that we kept pushing on. So let's look what we should get as we burn through that. So we have the plus sign, that's going to get pushed on. Then we push on the times. Is that allowed to go on?
Yeah.
Yes. Then we push on the divide. Is that allowed to go on?
No.
It's not. So that's going to fail. Then we push on the parentheses. So we're not doing anything with it right now. We just want to see if it's applying our rules correctly. So this guy's going to be gone in our current version of this. Is this guy allowed to go on top of a multiplication?
Yes.
Yep. He'll be allowed on there. Will this guy be allowed on there? Minus is not allowed on top of a closing parenthesis.
No.
Okay. Will this guy be, or an opening parenthesis?
No.
In our rules, he will be, but right now he won't be. Right.
Yeah.
A minus is allowed to go on top of an opening parenthesis in the future, but right now we should disallow it.
Mhm.
Okay. So we will not allow this. Will we allow that?
No.
We gave him a value of 1, right?
Yeah.
Power of 1, so he's not going to be allowed. Is this a guy? Is this guy allowed?
No.
Nope,
That is.
because he's a 4, which is less than the 5. This guy's also not allowed. So if our rules are being applied correctly right now, we should get a plus, a times, and an opening parenthesis. All right. Let's see here.
What is it?
Well, it's just complaining I didn't necessarily use those values. That's fine. There's no harm, no foul. So this is where I'm pushing those values. Curr token comes in. Let me toggle this guy off. It's got to be in our new push code here. Probably one of these guys is breaking. Let's put the breakpoint in right there. So we're going to get the payload from the head. When we push it. Unless the head is null. The very first thing we push is failing because we don't actually have a payload. So let's take, there, we'll just do this. if this dot head is equal to null, add it. Just treat it as a special case and be done with it. Otherwise, we were trying to get the index of the null value, of the payload of a null value. All right, so there's our values. So that's what we expected. Okay, so we're applying those rules correctly now. All right, fair enough. Okay, so now we need to finish applying those rules. If it comes back with a false, that means the thing I just tried to push is not allowed to be pushed, right? So what do I do? Let's go back here to our converter. Every single time I hit an operator, I'm going to try to push it onto the opstack. If I'm not allowed to push it onto the opstack, what happens? I need to pop off the opstack and add to the end of output and then try again. Does that make sense? So I need to try to do this. So while I try to push the current token onto the opstack, and while that guy fails, so while not this dot to the opstack dot push current token, while I cannot push him onto the opstack, what do I need to do? This dot the output dot addend, this dot remove, I'm sorry, this dot the opstack. Yeah, we currently have a remove front, which is effectively pop, right?
Yeah.
Okay, here, if we want to make ourselves feel better,
You just add.
public string pop return this dot remove front. That way it'll look correct to us, but they're synonyms for each other, right? So now we can say this dot pop. So we'll add to the end of our output the pop of our opstack, then do what? Try to add it again. Keep doing that until we finally can add it. Okay? Now, if curr token is a closing parenthesis, what does that say?
Pop everything until you find the opening parentheses.
If it's a closing parenthesis, I need to pop. I need to treat that as a special case, correct? So if curr token dot equals closing parenthesis, pop from opstack until we hit open parenthesis. Make sense? Okay. So we'll need to put that in there. Else, do this stuff. Okay, so we'll write the code for the pop here in a second, but we need to go back into our linked list and let's adjust how the opening parenthesis is working. Now that because we really want everything to be able to go on top of an opening parenthesis, right? We want everything to be able to land on top of that. So really, we need an opening parenthesis to have a position of weakness. Okay, but the problem is that we can't put a position of weakness on top of something else. So we need to have a way of adding to the front, forcing something onto the top of it. Okay? So we're going to give it a position of weakness here, but we need to treat it as the special case. So we're going to say if head is equal to null or op dot equals the opening parenthesis. If either of those things are true, if we're looking at the empty list, then we can push anything we want on there. Or if the op we're trying to push is an opening parenthesis, we're not checking the math. Push it. Does that make sense? We will always let opening parentheses go on there. And since opening parentheses now have a really low precedence, everything else will be allowed to pile on top of it. Make sense? So we don't need to mess with the math on that side. We just needed to get it on there. Okay? So now, back to our converter here. If we just read in a closing parenthesis, we need to pop until we get to an opening parenthesis and continue to push on to the output, or continue to add to the end of output. Make sense? So we'll go ahead and say, can we assume that we could probably do this as a do while, because we can assume that they're giving us legal things where they can't have an opening close parenthesis right next to each other. Fair enough?
Yes, it's legal.
Okay. So we'll say do string curr. We'll say curr is equal to this dot the opstack dot pop. Oh, you know what? This is a pretty good place for some bad programming.
All that.
Let me steal this. We'll go ahead and grab our current operator while curr dot equals opening, right? While that's not true, so while the operator we just read in is not a opening operator, we'll say this dot the output dot addend curr. And then we'll go ahead and read in the next guy. So pop off the operator stack. Since we just read in the closing, we're not going to do anything with that guy. He just lets us know we need to start popping. So we'll pop off the op stack. Then we'll ask the question, as long as what we just popped off is not the opening parenthesis, go ahead and add it to the end of our output. And then pop again. As soon as it is the end of the, as soon as it is the opening, we have removed it from the op stack, but we're not going to do anything with it. Right? Okay. So now, this is now our op stack display. Let's see what this guy looks like now. Okay, so now we have our, actually, hold on.
You missed the one power.
Power had a,
How about the display the output also?
the output dot display. Here's the output. 3, 4, 2 times 1, 5 minus 2 power
So still
Okay, so it let us get that. Why did it let us have the power? That's got to be a bug in this code. So that's 2, 2, 3, 3, 4. This guy has a value of 4. And we had 2 4s in a row, right? So when we got to here, this is plus, minus, times, divide. Okay, yeah, it's an R. So if new press is greater than top press, or new press is equal to top press, and top press is equal to, oh, it's not top press, it's top ass. Top ass. You got to get the right ass. Is that oh, this is awesome. All right, so there we go. Now we got the right things in there. Okay, so we hit the end. So now we're back here in converter. So after we've hit the end here, that means we've dealt with all of our tokens. And at that point, we need to go ahead and empty out our ops. We have processed all of the tokens. Now empty the opstack onto the output. So while this dot the opstack dot has more elements, this dot the output dot addend, this dot the opstack dot pop. And then the opstack should be empty, and then we'll go ahead and display output. So 3, 4, 2 times 1, 5 minus 2, 3 power slash plus. 3, 4, 2 times 1, 5 minus 3, 4, 2 times 1, 5 minus 2, 3 power slash plus. All right, so we've got it into reverse Polish now, right? Okay, so far so good. So that's most of the problem you had to solve. The processing it in math, once you have it in this format, is the easy part. Okay, so now we're going to go ahead and process this. So we have our converter, and the converter ultimately gives us the output. Let's go ahead and see what I call this guy, convert. Yeah, let's go ahead and, oh, we don't actually need it to return anything. It doesn't solve. We're just going to try to be fancy. All right, so he's not going to actually return anything, so that means we don't need this postfix thing. Ultimately, what he does is he turns the output into postfix, right? So then finally, we're going to have a public int. Well, it will be. Oh, the answer is going to be a double. Okay. So public double. Let's see. Process. Let's just call it process. This guy is going to walk through this, building up ops, doing stuff to whatever's in there. So we'll get the 3, we'll get the 4, we'll get the 2, then we do the times. What do we do with the times? We grab the 4 and 2. So we pop. So we're going to need a stack to do this. All right. So we're going to have a linked list called the process stack. This is going to be a new linked list. And what we're going to do is we're going to walk our output from left to right, popping each element off. If it's an operator, we're going to do something with it. If it's not an operator, we're going to keep it, push it on to the other guy. Okay? So, while this dot, the output dot, has more elements, what are we going to do with it? We're going to say, well, let's go ahead and give ourselves a string curr element. We'll say curr element is equal to this dot, the output dot pop. So we'll keep feeding off the front of this guy, right? Now we want to ask the question, is this an operator? If it's not an operator, meaning it's a number, I want to go ahead and just push it onto my process stack. So if this dot ops dot index of curr element is equal to a -1. If it was not found as an operator, then what am I going to do with it? What am I going to do with it? I'm going to say the process stack dot push. Now this guy's currently assuming it's an operator. Okay? So we really want to just keep adding to the front. So let's go in, give ourselves an add front here real quick. Public void add front if this dot head is equal to null, then this dot head is equal to, well, here we go. Front, this guy's going to take in a string value. Node n is equal to new node, built around value. This dot head is equal to n. Else, n dot set next node equal to this dot head, and then this dot head is equal to n. So that's our add front, which will function as our push because we already wrote a push that did all our specialty math stuff, right? So if this guy is a number, then we're going to say the process stack dot add front curr element. Else, I have an operator. It's either a plus, a minus, a times, divide, or a power, right? One of those guys. So no matter what it is, I'm going to be popping two things off the stack. Okay? They're the two operands. So operand 1, operand 2. We're going to consume those two values. All right, so let's go ahead and let's get, we'll work with it as doubles. Okay, so we'll say double op1 is equal to the process stack. Actually, we're going to do a double dot parse double the process stack dot pop, and then we'll have op2 is double dot parse double the process stack pop. So we'll get those two values. Now, if it's a plus, when we look at this guy down here, we did the 3, we did the 4, we did the 2, then we hit the multiplication. What are we multiplying? Is it 2 times 4 or is it 4 times 2? So we get an 8. Then we get a 1. Then we get a 5. Then we get a minus. Is this 1 minus 5 or is it 5 minus 1? 1 minus 5. All right. So this guy is 2 times 4.
No, 4 times 2.
4 times 2 rather. So this is pop. Well, let's go this way. So we push this onto the stack. We push this on top. We push this on top. So op1 will be the 2. Op2 will be the 4. You're telling me it is...
Up to times 2.
Okay, so it's the 4 times the 2. Just like this is the 1 minus the 5. So it's going to be op2 times op1. Okay? If curr element, it's a string, so if this guy dot equals a plus, then what are we going to do? We're going to say op2 plus op1 is going to give us an answer. That's a math answer, right? And what are we going to do with that math answer? We're going to turn it into a string. Okay? And then what are we going to do with that string? It's actually not going to be push. It's going to be dot, hang on, let me just steal this real quick. It's going to be dot add front. Oh, I didn't spell process stack right. That guy. So we'll do the math and then push the result back onto the process stack. As I was walking this here, I pushed 3 on, then I put the 4 on top of that, put the 2 on top of that. Now I hit the times. Time says pop off the 2, pop off the 4, multiply them together, push the 8 back on. Make sense? Okay? So do the math, push it back on the stack. So we'll steal this. Else if it's a minus, subtract. Else if it's a times, multiply. Else if it's a divide, then divide. Else if it's a power. I'm taking what to what power? Is it op2 to op1's power? Look down here. So right now the top of the stack is going to be a, so as we got to here, so we pushed on a 2, we pushed a 3 on top of that, right? So is this 3 to the second power, or is this 2 to the third power? Look at our original string here. It's 2 to the third power. Right? So is this op2 to the op1 power? Okay. Push it back onto the stack. All right, so we're going to keep doing this as long as what? The output has more elements. Okay? So in the end, all the way down here, when I'm done with this, this while loop, the while loop actually ends right here, right? I can go ahead and say system.out.println. Well, here, before I do that, let's just do, we'll print out the output. So the process stack dot display should have 1 element in it in the end, which should be our final answer. And what's the answer of this math? What should the answer of this be? I'll have it return a void for right now. Hold on. We never called process.
For the
So we'll take this out. Go into our driver. We'll convert and we'll process. Is that the right answer?
Yes.
Is that the right answer? Made a smaller, simpler one, right? 3 plus 4 times 2. So is this 7 times 2, or should this be 8 plus 3? Should be 8 plus 3. Should give us an 11. Make sense? All right. Questions. So does that solve the assignment?
Can you do like 4 times 22?
4 times 22, like this. So this should give us, what, 44, 88, so 91. All right, so based on our initial cursory testing, this seems to solve the problem. All right, so in the end, the complex part was what? Converting it to postfix. Once something is in postfix, processing it was actually pretty easy if we had a stack.
Yeah.
Does that make sense? I mean, most of this code we wrote here was just a bunch of if-else stuff, right? This guy down here was just, if it's a plus, do this. If it's a minus, do this, so on and so forth. All right, so we just made a calculator. Make sense? Okay. You like these variable names, the ass and top, what we had, top ass, and those are good variable names. I like those. All right. Okay, so questions about this at all? Let's go ahead and push it up to GitHub so we have it as a solution.
So Professor, can we use anything that we have studied in 535?
Yes.
Right. I thought I'm not supposed to use double also.
That's fine. So so you could solve it.
I use double, but in my self-assessment template, I have written like.
Here's the things I use that I didn't think I was allowed to use. Yeah. If you're ever in doubt, just ask.
Okay.
Throw up on Slack, say, hey, I'm trying to solve this problem. I'd like to use this. Am I allowed to use this? And I'll tell you whether you can use it or not. All right? Better safe than sorry.
I know you can use double. Otherwise you cannot get the answer.
All right, so let's do CSC537, fall 2015. What's this guy called? Shunting yard. Okay, so let's get into the right directory for that guy. All right, so I need to do cd space. Where do I keep it? Do I keep it in here? All right, so there is our answer. All right, under 2 hours.
Yeah. Very easy job.
All right, so let's take about a 45-second break.
Then how about the go directly?
Let's take 15 minutes. We'll come back. We'll talk about binary trees. So come back at 8:15.